That button. All right. All right, sorry, a couple minutes late here. Right, as a reminder, we have our second exam on Wednesday next week, a week from today. And we have the homework number 4 due this Friday. Okay. So yeah. So make sure, right, you've started working on homework number 4. That's due Friday. And again, that you are starting to get yourself ready for the exam in a week. Right. As a reminder, right, you know, when studying for the exam, look over homework questions, some answers. And I know the answers aren't detailed, but you can always come talk to me if you're not sure how I got the answer I got on the homework question. Right, and you can always look over the examples that we do in class. Most, if not almost all of the examples, right, have kind of roughly detailed solutions on the posted as well, right? Yeah. Yeah. So, any questions before we kind of get going today about related with the course? Whatever. We'll see how exam 2 goes. We've been getting like class most days recently, so I don't know. That means a lot of people have dropped the course, or which I doubt is very likely. Or yeah, we'll just see how this exam goes. So, all right. So we have been talking about starting to introduce ideas of mixtures, right? Last time we talked about talking about partial molar volumes and partial molar kind of chemical potentials, right? For mixtures of species, okay? And today we're going to talk about kind of some general thermodynamics of mixing of gases and solutions and relate that to ideal and ideal dilute solutions. Okay. Right, and then on Friday, we will talk about colligative properties. And then after the exam, we'll start talking about 2-component phase diagrams and things like that. And more, and go back again more talking about these ideal and ideal dilute solutions, and doing more kind of examples of those as well. And eventually that will lead to kind of discussions of distillation and how that works and other such things. Okay. All right. So open up the chat here. All right. So again, when we talk about the thermodynamics of mixing, right, we need to think about, if I want to talk about the Gibbs free energy change for mixing of two things, right, I want to think of potentially this relationship, right, how the change in Gibbs free energy is related to change in pressure, change in temperature, and change in number of moles, right? If I consider the mixing of two gases, right, at constant, right? So I'm right. If I'm mixing two gases, right, I'm going to assume I'm doing this mixture at constant temperature, right? I'm not trying to heat my gas or cool my gas at the same time I'm mixing them, right? I just have two gases that are in like separate compartments that didn't come together, right? So this mixture is being done at constant temperature, okay? Right, and obviously I'm not doing any chemical reactions or phase changes, so the composition is the same, right? So in that case, the Gibbs free energy change, right, is just related with the volume times the change in pressure, okay? So some final Gibbs free energy for this mixing is equal to the initial plus the integral of V dP, right? And so if I have an ideal gas, right, that change, right, that final Gibbs free energy is just related to initial plus nRT ln P final over P initial, right, using our simple ideal gas law. And this is a very, we've derived this equation like 3 times before, right? We've given this relationship between delta G and a change in pressure before for an ideal gas. Hopefully it looks familiar, okay? Right? And then we're just going to now use the fact that the chemical potential, right, is just the molar Gibbs free energy. How that Gibbs free energy changes with the change in number of moles, okay, right, to get that the chemical potential, right, that final chemical potential, say, is equal to the initial chemical potential plus RT ln of P final over P initial, right? And so this relationship tells us how the chemical potential of some gas changes with the change in pressure of that gas. Okay. Right, and so that relationship, right, this relationship between how the chemical potential changes with the change in pressure is something we'll use quite often. Okay. This will lead to a number of things. It will lead to kind of discussions of colligative properties and deriving those colligative property relationships that we've seen before in general chemistry. Okay. It will lead to something, right? When we eventually get chemical equilibrium, this relationship here, this change, this how the chemical potential changes in pressure, and I guess more often we'll use kind of this relationship, where we assume, say, the initial pressure is just 1 bar, okay, and then our chemical potential is the standard chemical potential. Okay? So this relationship, the chemical potential of a gas at some pressure related with its standard chemical potential plus RT ln of the whatever the pressure happens to be, okay, measured in bar, right? Again, the standard chemical potential is assuming 1 bar, so that pressure has got to be measured in bar, okay? Right, and we'll use that relationship eventually when we get to chemical equilibrium to derive the equilibrium constant expression, okay? Right, and so this relationship is going to be used quite a bit in the rest of this semester, where again we're talking about how the chemical potential of a gas changes with a change in pressure, which again is very important because, right, when talking about these phase diagrams, phase equilibrium, and chemical reactions and chemical equilibrium, and eventually talking about colligative properties, which is basically just related with how the vapor pressure of a liquid changes, right, with an addition of a solute, okay, right, and the fact that that vapor pressure is related to the boiling point and things of that nature for that liquid, okay, right, all of those things, right, are related again with the chemical potential, and when chemical potentials of certain substances are equal, right? So again, the vapor pressure of a liquid is when it is the pressure of the gas such that it equals the chemical potential of the liquid, right? That is what your vapor pressure of your liquid is, okay? Right, if you're to try to mathematically solve it, right, it's when the chemical potential of the molecules in the liquid phase equal to chemical potential of the molecules in the gas phase. And this relationship tells us how that chemical potential of the molecules in the gas phase relates to the pressure of that gas, right? Of that, say, that vapor pressure. Okay. So again, this formula here, I can't stress enough, is something that we'll use quite often, be very relevant and useful for our discussion, right? Now, again, this is assuming an ideal gas, right? But yeah, we will use that. Huh? Yeah, so the parentheses P here is just saying like chemical potential as a function of pressure. It's just trying to indicate, right, that this chemical potential is like a function of pressure, right? It's not like multiplying by P. Yeah, thank you, that. Right, the question is this mu parentheses P, is that saying it's chemical potential times pressure? No, that's just trying to indicate that's the chemical potential is a function of pressure, right? It depends on pressure, and how it depends on pressure is given as follows, right? You know, think of it like f of x, right? That's what it's trying to say in that expression. Okay. Yeah. All right. Right. So if I want to look at a mixture of two species, right? We know, right, from our discussion last time that the total Gibbs energy of that system of a mixture of two compounds, right, is just equal to the number of moles of a given species times its chemical potential, right, plus the number of moles of the other species times its chemical potential, and so on and so forth, right? That the total Gibbs energy of our system is equal to some of these chemical potentials times their total number of moles, right? If we consider what the Gibbs free energy is before I mix my gases, right? Again, it's that same expression, but it's the pure chemical potentials, right? It's the chemical potentials of the pure system, right? Which we're going to assume that both gases start off at the same initial pressure, calling it P, okay? So both gases start off on the same pressure P, right? So these pure chemical potentials are just their standard chemical potentials plus RT ln of P, where again, the initial pressures of the gases happen to be the same, okay? Right? And they happen to also be at the same temperature, okay? Right, so now if I mix these gases, assuming constant temperature conditions, right, the pressures of the gases are going to change, okay? As I mix them, right, they're in two separate containers. When I mix them, I have to change the volume of those gases. If the volume changes and the temperature is the same, number of moles are the same, right, pressure's got to change, right? So the pressure of A and B are going to change, and they're going to decrease, but we're going to mix them such that the total pressure in my system still remains a constant of P. Okay? So the total pressure is still that pressure P, okay? But the partial pressures have now been lowered because gases have now been expanded, right? Isothermal, essentially, right? Gases start off at some initial volume that's potentially different, right? But they're at the same pressure and they get isothermally expanded, the same final volume, and they end up at then different partial pressure. Okay. Right. And so then the energy change after mixing, right, is just the number of moles of A, which is the same number of moles of B, which is the same, times then the chemical potential of the mixed species, right? Which the chemical potential of the mixed species is just going to be the standard chemical potential plus RT ln of PA or RT ln of PB, right? The partial pressure of A or B, okay? And when you take the difference between that mixed free energy and the pure free energy, you will eventually arrive at this formula here. At the free energy change of mixing is just Na times RT ln of PA divided by P plus NB RT ln of PB divided by P. Right, and this free energy change of mixing of gases, right, this expression here is a fairly, I'll say narrow equation in terms of its applicability, right? You have to be doing an isothermal mixing of ideal gases that end up at the same final pressure. Okay. Right. or the gases, right, are being mixed in the same container such that the final total pressure is same between them, which is the same as their initial pressure, right? Here. Right, so again, right, this equation, right, delta G of mixing, if I use the fact that right, in the gas phase, the mole fraction of my gas is equal to the partial pressure of that gas divided by the total pressure, P, which again, P is the total pressure after mixing, right, which happens to be the total pressure before mixing as well, right? Yeah, that then this equation can simplify down to N here's the total number of moles, okay, times by the mole fraction of A times the natural log of the mole fraction of A plus the mole fraction of B times the natural log of the mole fraction of B. Okay? And again, this free energy change of mixing, which the highlighted equation here is the same as the equation up top. We're just using this definition of the mole fraction in the gas phase, right? Again, is only true if temperatures remain constant, the initial pressures of the two gases are equal, and the final pressure of the mixture is equal to the initial pressures of the gases, right? So again, it's kind of a narrow thing, right? But, right, often, right, if we're mixing gases in a lab and things like that, this is often what's done, right? That often your gases are at standard temperature pressure. And when you mix them, it's still at standard temperature pressure conditions, right? So typically when you mix gases, right, the total pressure in your system, in your container or whatever is still standard pressure. Okay. Often the case. So questions about this Gibbs free energy of mixing? Right, notice that this is always less than 0, which means, right, the mixing of any two ideal gases is always spontaneous, okay, right, which shouldn't be a big surprise, right? And again, it's always less than 0 because the mole fractions are always numbers less than 1, right? And the natural log of a number less than 1 is negative. Okay. So this expression is always going to be less than 0. Okay. All right. So when do you think you'll get kind of the maximum Gibbs free energy change for like what mole fraction of A, right? What type of mixture? Like a 75% mixture, 10, 80 or 90, 40, 60, 50, right? What type of a mixture, right, would you expect to have the maximum free energy change for mixing? When would we get the most mixing occurring between two ideal gases? What type of a mixture? A 50-50 mixture, right? Yeah. So the maximum free energy change is going to be for a 50-50 mixture, right? Because that's the most mixing that can occur, right? Mathematically, you could solve for that by using the fact that the mole fraction of B is just 1 minus the mole fraction of A, and then take the derivative of the entire thing with respect to the mole fraction of A and solve if you wanted to. And then you'd solve and find that the mole fraction of A is 0.5, right? But yeah, right, it's going to be a 50-50 mixture, right? Right, the equal composition of A and B will give you the most free energy change when you mix those things, right? Because again, that's just because you get the most mixing occur, right? Right, and then we talk about free energy. Now let's talk about entropy and enthalpy, right? Well, again, going back to this relationship with the Gibbs free energy, okay, right, and the fact that that change in Gibbs free energy is respect to change in temperature under constant pressure is related with negative of the entropy, okay? So under these constant temperature pressure conditions, right, again, the total pressure remained P in my entire mixing process, the total temperature remains T, right? We got this free energy change, okay, for the mixing given there, right? So take the derivative of this with respect to temperature, okay, and you get that the entropy change of mixing is just minus NR XA ln XA plus XB ln XB, right? Because again, that free energy change, the derivative with respect to temperature of that free energy change equals minus the entropy, so that's where that negative sign comes from, right? Right, so if you compare, right, that delta G and delta S, and the fact that, you know, under constant temperature conditions, right, delta G equals delta H minus T delta S, right? You can see here that delta H for mixing has to equal 0, right? That there is no enthalpy change for mixing, right? This is purely an entropy-driven process for the mixing of two ideal gases, right? And why is that the case? Why is it for the mixing of two ideal gases that the free energy change, right, that mixing is purely driven just by entropy and not by enthalpy? What makes something an ideal gas? No intermolecular forces, right? So I can't get some sort of enthalpy or internal energy change when mixing gases. They don't interact with each other, right? Like they have no interaction with each other whatsoever, right? So mixing of those ideal gases, right, under constant temperature conditions has got to be an enthalpy change of 0, right? Because again, each of these ideal gases, you're just isothermally expanding the gas, right? Which an isothermal expansion for an ideal gas has an enthalpy change of 0, right? And so yeah, so for ideal gases, right, that you should expect that it's only entropy that's driving this mixing, because again, there's no intermolecular forces, so there can't be any enthalpy changes, right? Can't be any energy changes, and so it's purely just an entropy process. Okay. So questions about the thermodynamics of mixing of two ideal gases. So I have a container divided into two equal volume compartments. One compartment contains 3 moles of H2, and the other contains 1 mole of N2. They're both at 25 degrees Celsius. We're going to assume ideal gas behavior and isothermal conditions. We want to know what is the given energy and entropy of mixing when the partition is removed. All right. Here. Okay. Right. So I have a situation here where I am mixing, right, 3 moles of H2 and 1 mole of N2 together, right, where they happen to be at the same initial volume, okay, for this mixing, right? So the volume, right, goes, you know, the initial volume, I guess the final volume, right, is just 2 times the initial volume, right, is essentially what's going on in this problem, okay? Right? And so, right, if we think of the pressure of H2, right, the final pressure of H2, right, is just going to be 1/2 the initial pressure of H2. And same thing with the final pressure, of N2. Try that again. P N2 final, right? It's just initial times 1/2, right? Because again, right, the temperature is staying constant at 298 Kelvin, right? And if my volume has doubled, my pressure has to decrease by 1/2 for these 2 gases, right? Okay. Right, but in this problem, right, it's not quite the same as that previous problem we had where it was just like the mole, right, where that free energy change mixing happened to just be the mole fractions of the species, right? Because in this problem, right, the initial pressures do not equal on both sides of the container, right? And they aren't the same as the final pressure, right? So over here, right, my Gibbs free energy initially, okay, is number of moles of H2, right? So we can kind of do what was done in the example in class. A little different here. So number of moles of H2 times the chemical potential of H2 plus number of moles of N2 times the chemical potential of N2, okay? Right, which this is number of moles of H2 times mu H2 naught plus RT/ln of P initial H2, right? And this is plus number of moles of N2 mu N2 naught plus RT/ln P N2 initial. Right. Right, the initial chemical potential of H2 and N2 are just going to be related with their initial pressures, okay, which aren't necessarily the same, right? I mean, we know they're not the same, okay, because the volumes are different, right? And the volumes are the same, but the number of moles are different, right? So I could actually tell you that the pressure in the side that contains H2 is 3 times larger than the pressure in the side that contains N2. It's got 3 times more moles in the same amount of volume, right? And these are just ideal gases. So it does not matter if I call it H2, N2, or whatever, right? 3 moles of an ideal gas has 3 times the pressure of 1 mole of an ideal gas under the same volume temperature conditions, right? Okay. So I can even like make that note and we'll see if it will be relevant, right? But P initial or P N2 initial, right, related to P H2 initial, right, is 3, right? 3 times P N2 initial is equal to P H2 initial, okay? Right? And we know this, again, just using the idea of PV equals nRT, right? For an ideal gas, if volume and temperature are the same between these 2 gases, right? I've tripled the number of moles. That means I have to triple the pressure, okay? All right. So in the Gibbs free energy after mixing, right, is going to be this NH2 times its standard chemical potential, right, plus RT/ln PH2 final plus N2 times its standard chemical potential plus RT/ln of PN2 final, okay? Right? And so again, in this problem, right, I'm just thinking about what's going on, right? I have these 2 separate compartments, right, of these ideal gases that happen to be at the same volume, okay? knowing that they're the same volume, right, tells me when I open up the divider between these compartments, the volumes for each gas doubles. So the pressure for each gas is going to have to go down by a half because it's an isothermal expansion, right? Right, and then I know the relationship between the pressures of the gases, which may or may not be relevant. Okay? And I want to know, again, what is the free energy change of mixing, right? Which is just going to basically be what is the difference in the free energy after I mix the gases versus before I mix the gases, right? And so delta G mix, right? Try to zoom out a little bit here, right? Trying to keep all this stuff here. Right, delta G mix is just G final minus G initial, right? Which, if you notice, right, then those standard chemical potentials cancel with each other, so we don't need to worry about those, right? And it's just the number of moles of H2 times RT ln of what do we got here? P H2 final over PH2 initial plus number of moles of N2 times RT ln PN2 final over PN2 initial. Okay. All right. Sorry, my handwriting not the greatest, but that's initial pressure, final pressure of N2, right? Initial pressure, final pressure of H2, okay? And then just multiplied right by their number of moles, okay? And so, right, this, using the fact that we know these pressures, right, decrease by a half, right, just makes each one of these natural logs just be 1/2, right? The natural log of a half, right? So it's delta G of mixing, right, is just equal to the number of moles of H2 is 3 moles, right? R is 8.314, temperature is 298 Kelvin, and then this is the natural log of 1/2 plus 1 mole times 8.314 times 298 Kelvin times natural log of 1/2, right? And so plugging in those numbers will give us that free energy change of mixing, right? And the final number we'll get by going back to the slides real quick, but I'll wait to go back to the slides to just ask any questions about what we did, why we did it, how we did it. What the heck is that scribble on that piece of paper there supposed to mean? Right.
I have a question.
Yep.
So the reason you know that the pressure is halved is because once the divider is removed, the volume is doubled, and is that why?
Yeah.
Okay.
Yeah, exactly. We know that because, again, in the problem it says that these gases are in equal volume containers, like the volume of the gases are equal initially. So we know we have this kind of a setup where I have the same like initial volume. I can call this like VI, right? So that once I remove this divider, right, the final volume is just 2 times the initial volume. And, you know, our ideal gas law, right, if the number of moles are staying the same, right, R is staying the same, T is staying the same, right, if the volume doubles, pressure's got to go down by a half, right? And so that's how I know that the final pressure of these 2 gases is just half of their initial pressure, just by using that relationship for an ideal gas. Other questions? Yeah.
What happens to mu for the change in G mixture? Like, where does that go? Like in G final we have NH.
Mu naught, though, like the standard. Yeah. Well, basically because that standard chemical potential, right, is the same initially and finally in the mixtures. And so they cancel with each other, right? So this cancels that term when I take the difference, because the number of moles are the same of H2. So the number of moles of H2 times its standard chemical potential at 1 bar cancels with each other. So which this will happen quite often when we talk about different questions and things like that, where, you know, because in this class we care about changes in Gibbs free energy, changes in enthalpy, changes in things, right? Right, these standard chemical potentials will cancel with each other, and we never really need to know what they actually are. So. Calculating changes, relative quantities are very, very nice. All right, so going back, slide here. Let's see if I did the same in the slide. Oh, so let's see, final pressure into. Okay, so for here I called like just the pressure, some pressure P, right? So I called the initial pressure of N2P and final pressure, initial pressure of H2P. Then I used like P and everything, but I think I end up getting the same expression. Yeah, 1/2, 1/2, right? Yeah. So the same thing. I just decided to like plug in for what these pressures are in terms of just some value P. But yeah. Yeah. So that's the Gibbs free energy change of mixing, right? And the entropy change is just the Gibbs free energy minus or divided by the temperature, 298, right? And then the negative of that, you get 9.7. So this should be the negative of the negative 6.9, right? So I like dropped the minus sign here in that expression right there. I guess I can change that real quick. Right, this should be negative. Right. That'll kind of make a little bit more sense, right? It's the negative of the free energy change, which happens to be negative 6.9 kilojoules, right? Divided by temperature 298 Kelvin. So it gives you a positive 9.7 joules per Kelvin, right? Which entropy change of mixing should be positive, right? Because I should have an increase in entropy when I mix two things, right? As things get more disordered, every time something gets more disordered, entropy should be increasing, right? So again, that entropy change should be positive. We should never get a negative entropy change when mixing two compounds. Not possible. Okay? You can get a positive free energy change when mixing two species, assuming they're non-ideal, because the enthalpy can be potentially non-zero for a real system mixing, right? Right. I mean, that happens all the time with mixing of a solid and a solution, right? Where you can have an endothermic or an exothermic mixing, right? Or dissolving, right? Dissolving some solid in a liquid is mixing two things together, right? And the dissolution process can be endothermic or exothermic, right? I mean, and when we have applications of those things all the time, right? Heating, cooling packs, right, that work by like, you know, breaking some barrier between things and mixing them together, right? Those just use the fact that the enthalpy or of those mixing processes are either exothermic or endothermic, right? Yeah. Yeah. So R is given in joules. Right, so I didn't write out the numbers here, but R is given in joules, temperatures, and Kelvin, right? But basically 8.314 times 298, and the logarithm of 1/2 is negative logarithm of 2, which is 0.69. So if you multiply all that out, you'll get like 6,900 something joules. And I just, yeah. So here I didn't even show it the actual numbers R and T and things like that in the slides. To do it right. So in my written out stuff, right, this would give me like a negative 6,900, you know, joules, right, and then convert to kilojoules, right, I just divide it by 1,000. So did I get a different number than what you got?
I got 6869, which is fine for that. But how do you do the math on the delta S? Because 6900 divided by 298 is 7.
No. All right. So then I guess what is that then? What's 6?
23.05.
Okay. Yeah, so I don't know. I guess I did that wrong. So this comes out to be 23 joules per Kelvin roughly.
Yeah, 23.05.
All right, so yeah, that was just typo on my part. So 23 joules per Kelvin. Okay. All right. Other questions? Yep.
Did you get the same answer for the mixing and conditioning like formula you do with there? It's like not all the same like conditions for the pressure have an equal forecast.
No, so you won't get the same entropy or Gibbs energy of mixing if you use that formula that we just kind of, derived here in terms of like mole fractions, because it like basically like everything out front kind of works like NR and the mole fractions of A and B and stuff are fine, but what you're taking the natural log of is not the same. It won't be the natural log of A and natural log, like, right? Because if you did that formula, you would have like total number of moles is 4, so you do like XA would be right, like 3 divided by 4, and XB, let's say that's nitrogen, would be 1 divided by 4, right? And all that would be kind of fine, but then you do the natural log of 1/4 and the natural log of 3/4 and stuff like that, which is not the same thing as what the actual problem is, where it's the natural log of a half and the natural log of a half. No problem. So yeah, so you won't get the same answer if you use that formula, right? Again, that formula is very specific to the type of problem that it was given, where the pressures are the same between both gases initially, and that equals the final pressure of the system.
So that mole fraction equation is just like if they're in the container, just half of be separated, and then they make the barrier, they have to be sitting in.
Yeah, I mean, so I mean, why we talk about it is because, again, like, it will pop back up when you're talking about mixing of ideal solutions, okay? And that, I guess that's kind of why we bring it up now for gases, is because they'll end up applying to the mixture of ideal solutions, which in that case for ideal solutions, it's a lot more applicable to any ideal solution, any solution that you treat as an ideal one that works. It doesn't worry about like pressures and crap like that, because you don't have to worry about pressures of the liquids and stuff, right? So yeah, so it's that equation is more applicable in the end when you talk about mixtures of ideal solutions. But yeah, and like in lab, it's not unreasonable to potentially think you have 2 potential gases that you're mixing that are at the same like standard temperature pressure conditions like that, right? And not necessarily at the same volumes or things like that, right? But yeah. But yeah, so we'll see that exact same equation right now as we talk about ideal solutions. Okay, again is where kind of that equation becomes more generally relevant. Okay, so let's consider, right, for an ideal solution. Let's consider first just the chemical potential of a pure solution. I'm going to call mu A star, and that pure solution at a given temperature, right, is going to have some vapor pressure. I'm going to call PA star, right? So PA star is the vapor pressure of the pure liquid, right? The pure solvent, let's say, right? Which has a pure solvent chemical potential of mu A star, right? And again, the chemical potential of a liquid, right? Right, is equal to the chemical potential of its vapor, right? Given the vapor pressure, right? So the chemical potential and the chemical potential of a vapor is just its standard chemical potential at 1 bar plus RT ln of its pressure, right? So the chemical potential of some pure liquid is equal to the chemical potential at standard temperature pressure conditions plus RT ln of the vapor pressure of that liquid. Okay. All right, again, I get this equation for the chemical potential of a pure liquid, of a pure solvent, again, by using the fact that I know that the chemical potential of the vapor, when the vapor has a pressure equal to the vapor pressure of that gas, right, is meaning that it's at equilibrium, right? Because again, talking about the vapor pressure of a liquid is the vapor above that liquid when the vapor is in equilibrium with the liquid. Right? That is the definition of the vapor pressure, right? Is that you have an established equilibrium between the gas phase molecules and the liquid phase molecules, right? Which means if an equilibrium is established between them, that their chemical potentials are equal. Okay? So the chemical potential of the liquid, of the solvent, is just equal to the chemical potential of the vapor, right? Which is just given by this mu naught plus RT ln of the vapor pressure, right? Which we just talked about. Okay? Right? Now, if I mix something in the liquid, right, add some solute, maybe it's a solid, maybe it's another liquid, whatever it is, right? The chemical potential of that liquid is still going to be related with the chemical potential of its vapor pressure, right? It's just now the vapor pressure of the liquid is different than the pure liquid, right, pure solvent vapor pressure, right? So the only thing that changes, right, for the chemical potential of the liquid is the fact that its vapor pressure changes, right? Its vapor pressure changes, and so that tells me how the chemical potential of the liquid changes, right? Because again, right, the vapor pressure is the pressure that you have above your liquid when the chemical potential of that vapor equals that of the liquid, right? So I can sort of measure how the liquid chemical potential changes by measuring, right, how the gas chemical potential changes. I can get how the gas chemical potential changes by looking at how its pressure changes. Again, I have this relationship pressure of a gas and its chemical potential, right? Okay. So the change in vapor pressure gives us the change in chemical potential of the liquid, okay? Right? So if I subtract these two equations, okay, what you get is that the chemical potential of some mixture, right? Okay, so the chemical potential of A in some mixture is equal to its chemical potential of just pure A plus RT times the natural log of the vapor pressure of A in the mixture divided by the vapor pressure of A, pure A, right? The pure solvent. Okay? And this relationship we'll use on Friday again when talking about colligative properties. Okay? We'll use it here in talking about an ideal dilute solution. Okay? And this is in general true for any liquid, okay, any liquid mixtures, right? Real, ideal, whatever, right? That the chemical potential of the mixture, right, of A is related to its pure chemical potential plus RT times the natural log of the vapor pressure of A in the mixture divided by the vapor pressure of A for the pure solvent. All right. So for an ideal solution, okay, we are going to assume that the liquid obeys Raoult's law, okay, which you may or may not have been told Raoult's law in general chemistry or some other types of chemistry. If anyone, how many people have heard of Raoult's law? A couple. I know I don't mention it in my Gen Chem class, but you know, right? And maybe some other class you've heard of, right? But Raoult's law just states, and it's an approximation. Raoult's approximation, which states that the chemical potential, or sorry, not the chemical potential, that the mole fraction in the solution phase of species A is just equal to the vapor pressure of A divided by its pure vapor pressure. Okay, right? This rough formula here, right? That P of A is equal to chi A P A star, right? Should look somewhat familiar, right? It's kind of like the same type of formula that the partial pressure of A equals the mole fraction of A times the total pressure. Okay, but that mole fraction is in the gas phase. Okay, here I'm relating the vapor pressure of a liquid to the mole fraction in the liquid phase, right? So when we talk about two mixtures and phase diagrams and things like that after the exam, we'll be talking about mole fractions in the liquid phase and in the vapor phase, and we'll often use chi A or XA as the mole fraction in the liquid phase and YA as the mole fraction in the vapor phase. Okay, so again, note here that that expression like the P partial pressure of A equals the mole fraction in the gas phase times the total pressure, that is true if that mole fraction is the gas phase mole fraction, and that's true for ideal or non-ideal gases, it's true always. But you need to know what is the mole fraction in the gas phase. Okay? But here I'm talking about knowing the mole fraction in the solution phase and how that relates to its vapor pressure. Okay? And so again, this is an approximation that the mole fraction in the solution phase times the vapor pressure of the pure solvent gives me the vapor pressure in the of the mixture. Okay, which is just saying, as my mixture goes from 100% of my solvent to 0%, of my solvent, I just have this linear change in vapor pressure according to the mole fraction, So I just have this linear decrease or increase as, say, the mole fraction of A, increases, then the partial pressure B decreases, or the partial pressure of A increases, just according to the mole fraction times its pure vapor pressure. Okay. And so the total pressure ends up just being kind of a linear line between the vapor pressure of A and the vapor pressure of B, in some mixture. Okay. If I add up these two blue lines, I will get the black line here, okay. And the partial pressure of A plus the partial pressure of B equaling the total pressure, that's always true. But this equation up here, partial pressure of A being the mole fraction of A in the liquid phase times its partial pressure of the pure liquid, or vapor pressure, of the pure liquid, That equation for A and B is, again, an approximation, and that approximation is related to Raoult's law, okay? Essentially called Raoult's law, that approximation, okay? And that is, and if I assume an ideal solution, then that is valid, An ideal solution is assuming this, okay? And so if I use Raoult's law, okay, then what I get is that the chemical potential of my mixture equals the chemical potential of the pure species plus RT times the natural log of the mole fraction of A in the solution. Okay, and this is true only for Raoult's law for an ideal solution. Okay, an example of this is, say, benzene with methylbenzene. Okay, where the mixture of these two things, gives you almost an ideal solution, Because benzene and methylbenzene are almost the same type of mole, They have almost exact same intermolecular forces, and that's really where it comes down to. Talk about Henry's law. Here we go. Oh crap! I thought I had a slide here on it. I guess not. But basically, an ideal solution assumes that the intermolecular forces that exist between molecules A and molecules B and B are the same, and they're the same between molecules A and B, That all intermolecular forces are the same, That molecules A and B all have the exact same intermolecular forces, So that the interactions between A and B, A and A, and B are all the exact same. That is an ideal solution, So it's not, An ideal gas states that there's no intermolecular forces, I can't have zero intermolecular forces for a liquid, otherwise it won't exist as a liquid, So you're not assuming for an ideal solution that the liquid has no intermolecular forces. An ideal solution just assumes the intermolecular forces in the entire solution between all components in the solution are the exact same. Okay? In that assumption, then Raoult's law is obeyed, okay? Because then the vapor pressure just depends on how much of that substance you have, in a non-ideal solution, okay, to show some examples of, if the intermolecular forces between A and B are, say, stronger than that between A and A, when I add B into my solution, it's going to try to hold those A molecules in that solution more, and that's going to lower the vapor pressure more than it would in an ideal solution, in an ideal case, right? Because the intermolecular forces are containing molecules in the liquid phase, right? If the intermolecular forces increase, and so that's going to reduce your vapor pressure for, say, A, okay? And so again, this relationship between in Raoult's law, between the chemical potential, or not chemical potential, like I'm saying that, between the mole fraction in the liquid phase and the vapor pressure, right, is assuming intermolecular forces between molecules A and B are the same as they are between A and B and B. Okay. And again, this is an example of a solution that happens to obey Raoult's law for the entire mole fraction, but this is a very rare thing. Okay, there are not a lot of solutions that obey Raoult's law for the entire mixture, but Raoult's law is a great approximation for a solvent in a dilute solution. Okay, so right, a dilute solution where the mole fraction of the solute is very small, then the solvent obeys Raoult's law. Okay, and so that's related with ideal dilute solutions. Okay, so an ideal dilute solution is defined as a solution where the solvent obeys Raoult's law and the solute obeys Henry's law. Okay, Henry's law is the exact same type of expression as Raoult's law, except instead of the vapor pressure of the pure liquid, it is this Henry's law constant, which is some empirical thing. Okay, right? Henry's law constant is an empirical number. Okay, it's often different than the pure vapor pressure of that species, and then often you get it by extrapolating the plot of the pressure of, say, B versus its mole fraction when the mole fraction goes towards 0. Okay, so for example, okay, the mole fraction of carbon disulfide, right, in a carbon disulfide acetone mixture, right, see here that the vapor pressures of these things do not follow the same kind of linear relationship, right? They're very different, and that's because the intermolecular forces are different between acetone and carbon disulfide, okay? Right, and so that total pressure is also a nice linear looking thing, okay? But if you look, right, here, okay, well, so this is different. This is acetone and chloroform, right? But this is another non-ideal solution, right? But if you look at these non-ideal solutions, what you'll see is near 100, mole fraction of 1 and a mole fraction of 0, the vapor pressures of both the solute and the solvent, right, okay, are roughly linear. Okay, so these things are roughly linear near mole fractions of 0 and near mole fractions of 1. Okay, and so that linearity, right, is either related with Raoult's law or Henry's law. Okay, right, which again, Henry's law is the mole fraction, the mole fraction in the liquid phase times Henry's law constant gives you that vapor pressure. Okay, right. So again, K here, say the Henry's law constant for acetone, right, which again here I'm plotting the mole fraction of chloroform. So here the mole fraction of acetone is very, very small, and so its vapor pressure obeys Henry's law, okay, which is just the mole fraction times Henry's law constant. But when the mole fraction of chloroform is very small, mole fraction of acetone is very large, and that's our solvent. So it's going to obey Raoult's law, right, which is going to be that the mole fraction times the pure vapor pressure of acetone, right? Okay. And so, right, this mixture, like every mixture, is going to obey Raoult's law for dilute solutions for the solvent, okay? And it's going to obey Henry's law for the solute in the dilute solution, right? Which again, for a dilute solution here, say the mole fraction of chloroform is near 0, right? Chloroform is the solute, and acetone is the solvent, right? Which again, chloroform obeys Henry's law near a mole fraction of 0, and acetone obeys Raoult's law for a mole fraction near 0 of chloroform. Okay. Right. Again, the Henry's law constants are just, right, this, whatever this value is, like 175, right, and 170 or something like that, right? Again, they're just extrapolated out. for these guys, right? So you just take a linear, take that, near zero slope and draw it as a straight line and extrapolate it to get Henry's law constant for that given liquid, right? Which again, Henry's law constant is going to depend on the liquid itself, right? It's different for each liquid. That's to be determined empirically for every liquid. Okay? So questions about what is an ideal dilute solution? Okay, what is an ideal solution? Henry's law, Raoult's law. Okay, right. So using, say, Henry's law, or to get the chemical potential right, it would just chemical potential of your, say, of your solute equals the chemical potential plus RT. Well, actually, so you wouldn't use XA here. You'd have to, yeah, it would be like the mole fraction of the solute times Henry's law constant divided by the vapor pressure of the pure solute, right? So it's actually kind of a more annoying form than that. If I have it written out somewhere, I don't think so. No. Yeah, I don't have it written out because it's not really a nice formula to use, but yeah. So any questions about this stuff? What makes an ideal solution an ideal dilute solution? And there's law of Raoult's law. So which of the following is not true for the mixing of two ideal gases at constant temperature and pressure? Delta H is 0, delta S is 0, delta G is less than 0, delta mu is less than 0. All of these are true. B, right? B is not true, right? Entropy does definitely change, and it's greater than 0 for the mixture of two ideal gases under constant temperature pressure conditions. Okay? For Raoult's law, most real solutions obey Raoult's law closely in all compositions. The vapor pressure of a liquid is equal to its mole fraction in the vapor phase times its pure vapor pressure. PA, vapor pressure equals mole fraction A times total vapor pressure, okay? Or total pressure, sorry, right? All of these are true, or only two of them are true, or all three are false. So B, they're all false. B, the reason why it's false, so let's go through these, right? A is false because most real solutions do not obey Raoult's law. Otherwise, they wouldn't be, right, solutions that obey Raoult's law wouldn't be called ideal solutions, right? Ideal solutions, all ideal solutions obey Raoult's law, but all real solutions definitely do not follow Raoult's law for all compositions, right? All real solutions follow Raoult's law for very low mole fractions of the solute if you're looking at the solvent, right? So the solvent obeys Raoult's law in all real solutions for very dilute solutions, okay? Right? So for B here, right, it's almost true, except you're looking at the mole fraction in the liquid phase, not the mole fraction in the vapor phase, right? And C is true if you're talking about the mole fraction in the vapor phase. But again, chi A is, we're going to use this relationship, chi A is the mole fraction in the liquid phase, okay? But C would be true, assuming you're talking about the mole fraction in the vapor phase, right? So yeah. So like potentially I would have accepted, say, C, since I wasn't very specific saying that chi A, right, is the mole fraction in the liquid phase. But again, I'm trying to hammer home that point that we will use chi A or XA, right, as the mole fraction in the liquid phase, and we'll start using Y sub A as the mole fraction in the vapor phase when we talk about these mixtures of liquids and things like that, because we will talk about mole fractions in the liquid and vapor phase, and they will be different from each other, okay, right? Right, the mole fractions in the liquid phase and the vapor phase will not be the same for almost all cases, right? All right, assuming ideal behavior for gases, which of the following is false? A, B, C, or D, or is it E, more than one, or F, all statements are true? Meaning all four statements, not necessarily that A, B, C, D, and E are true, right? But all four statements. Yeah, so D here is the false and only false statement, because Raoult's law is usually a good approximation or a good description of the solvent in a dilute solution, right? Henry's law is a good approximation for the solute in a dilute solution. Raoult's law is a good approximation for the solvent. Yeah.
Are we gonna be given a Henry's law of constant?
Yeah. No. I don't know what those are. Right? Yeah. No, you'd be given your Henry's law constants. You'd be given vapor pressures of pure liquids and things like that. Yeah. Right. You need to know what Henry's law and Raoult's law is. Pretty simple equations to remember, but okay. But yeah, you don't need to know what those constants actually are, for sure. Any other questions about this question here? All right. All right, so often you can use Henry's law to talk about dissolved gases and liquid solvents, because often the concentration of those gases in a liquid are very, very dilute. Okay? So the solubility of O2, right, at 25, we're trying to estimate the molar solubility of O2 at 25 degrees Celsius, given the fact that the atmospheric partial pressure of O2 is 0.16 torr, okay? And Henry's law constant is 3.3 times 10 to the 7 torr. And given the fact that density of water is 1 grams per centimeter cubed. Oh, shoot. All right. One. Oh, let me fix it here. So one minor note, it's not 0.16 torr, it's 160 torr. Felt like that seemed like a small pressure here. Right. So, right. Right, what we're asked for, right, is what is the concentration of O2 in water, right, which is the moles of O2 over the volume of H2O, right? Right, that is our concentration of O2, right, definition, okay? So that's what we're looking for, right? So we need to somehow get that ratio, that relationship, okay? And we know, right, that this gas obeys Henry's law so that the Sorry, I just heard something. Someone say something?
There's a chair.
Oh, all right. Right, so we know that the pressure of O2, the vapor pressure of O2 above the liquid, right, has to equal the mole fraction of O2 times Henry's law constant, right? The mole fraction of O2 in the liquid phase, right? Right? Now this is true, right? So right, what we have here is we have air, right, sitting above our water, right, say in the ocean, right? So air's, atmospheric pressure of air is above ocean water, right? That is going to come in equilibrium with some amount of O2 being dissolved in that water, right? So the pressure of the O2 is related with what its mole fraction is in the solution phase, right? Right. Some mole fraction of O2 in the solution phase is going to be related with the total pressure of O2 above the liquid. And that relationship is given by Henry's law constant, right? And then I can use the mole fraction of O2, right? Because the mole fraction of O2 is the moles of O2 over N total, right? So I can use the mole fraction of O2 to get to the concentration of O2. Okay, so the first thing is I need to solve for the mole fraction of O2. So I take mole fraction of O2 is just equal to the pressure of O2 divided by Henry's law constant for O2, okay, which is that 160 torr divided by 3.3 times 10 to the 7 torr. Okay, so that's the mole fraction of O2, right? And to relate the mole fraction of O2 to the concentration of O2, I'm going to use the fact, right? So right, the mole fraction of O2 equals NO2 over NO2 plus NH2O, right? And so so you could do this without assuming some total volume of solution, okay? But it will make life a little bit easier if we do assume a total volume, okay? Well, I will approximate this, and we'll see it's a very reasonable approximation, that this mole fraction, right, is roughly NO2 over NH2O, okay? That makes our life a little bit easier, right? So if I make this assumption, right, the number of moles of O2 divided by number of moles of H2O is the mole fraction of O2, right? I basically write the number of moles of O2 plus the number of moles of H2O, which is just going to be basically the number of moles of H2O. Okay. Right. And it's a reasonable approximation because, right, 160 divided by 3.3 times 10 to the 7 is like something times 10 to the minus 6. Okay. Huh? Right. So this is 4.8 times 10 to the minus 6, right? So it's a really small mole fraction, right? Which tells you, right, the number of moles compared to of O2 compared to the number of moles of H2O is very, very small, right? So this is a fine approximation, right? And then I can take the number of moles of H2O, right? If I take the number of moles of H2O and I, molecular weights, multiply by the molecular weight, right? Which gives me the molecular weight, which is 18 roughly grams per mole, right? And that gives me grams. And then I divide it by the density, which is 1 gram per milliliter, right? And then I take that and I convert, right, 1,000 milliliters in 1 liter, right? Right. So if I take the number of moles, multiply by these conversion factors, right, this will give me the volume of H2O. Oh, that's kind of off the top of the paper, right? So the number of moles of H2O times its molecular weight to convert it to grams, divided by its density, convert it to milliliters, then convert that to liters, will give me the volume of H2O in liters. Okay. And then I can just take, right, that volume of H2O in liters. So what do I got to do here? So this volume of H2O, trying to think of like, right, without assuming anything, what we have to do then is take this conversion. H2O, cancel that. Okay, there we go. So I'm trying to do this without assuming a total volume. a little bit more difficult. But so mole fractions of O2 equals number of moles of O2, right? And then given this relationship, right, the number of moles of H2O times all this equals that, right? So that tells me the number of moles of H2O equals the volume of H2O, right? Divided by 18, right, and multiplied by 1,000. Okay, so if I just move all of this on to the other side of this equation, right, so all of this equals the volume of H2O. Okay, so I move all of this over to the left-hand side to get the number of moles of H2O is equal to the volume of H2O times that stuff, right? Then I can plug that into the denominator here, my mole fraction, the volume H2O times 1,000 divided by 18, okay? Which this is equal, number of moles of H2O, number of moles of O2 divided by the volume of H2O is the concentration of O2, right? Times 1 over 1,000 divided by 18, right? So move that onto the other side to get the concentration of O2 equals the mole fraction O2 times 1,000 divided by 18. Okay. And that will give you the concentration of O2. Now, I did all of this without assuming a total volume. You can make your life a whole hell of a lot easier if you assume, say, like 1 mole of water or 1 liter of water or something like that, and then use that to convert to concentration. Okay. But you can do this without assuming some total amount. So if I have, right, so I did this relationship. Okay, so I actually did this exact same thing in the slide without assuming a total amount, right? But you get the concentration of O2 is 2.69 times 10⁻⁴ moles per liter. Okay? But again, you could, if you assumed a total volume of water, you know, you could have then used that and the mole fraction to find out whether the total moles of O2 is in that total volume of water, and then got the concentration. Yeah.
Moles of O2 is just 1 mole total minus mole fraction of O2.
Here, so and O2.
Mole fraction of O2.
So I'm confused. So the number of moles of O2 is equal to what? Are you saying?
You can find number of moles of O2 by the 165 by K, but then 1 minus that gives you moles of H2O.
I mean the mole fraction of H2O. Right. One minus the mole fraction of O2 gives you the mole fraction of H2O.
Well, yeah, but so that's that X of O2 is yeah. So it's 4.85 times 10 to the negative 6 moles of O2 per mole total.
Right. That's what you're saying, right? This. That's the relationship you're talking about.
1 mole total.
Yeah, so if you assume 1 mole total, yeah. So that's what I'm saying. If you assume some like total moles or you assume some total volume, then you like can do this a lot more just kind of straightforward math-wise without having to like rearrange all these conversions.
That's what I did. I got literally did that.
Yeah, you will, right? Because right. So once we found the mole fraction of O2, converting that to a concentration is literally just changing from like Celsius to Fahrenheit or atmospheres to bars or things like that, right? You're just changing like your units, right? And so, right, it's just when you're changing concentration units, if you don't assume a total amount, right, it's just more kind of annoying to work it out. But if you assume a total amount, then it makes doing the math a lot easier. So yeah. When I do this in general chemistry, I tell them assume a total amount. I never go through this process in Gen Chem. I say, listen, just assume like 1 mole of this or 1 liter of this and use that. I promise you, no matter what you assume, you get the exact same answer. And it's true, right? No matter what you, right? Because we're assuming these are homogeneous mixtures, right? So no matter how much you assume of something, right, the mixture is the same as what any other assumption of the total amount, right? It does not, the concentration does not depend on the total amount of stuff. Yeah. There you go. But by the way, so class period is technically over. So if you need to go, you're welcome to go. All right. But if you have further questions, say about this example or things like that, I'm happy to go over it, talk about it. So yeah. Remember, again, homework due Friday in 2 days. Yeah, no, it really is. It is so much easier if you assume some amount. Which again is why I tell everyone in general chemistry to do that. Yeah. Yeah. Well, I don't know. I just, you know, this is an upper level class.